Yes.
So, did you write something on your computer so we can share your screen, or you want me to work here?
I write on my notebook.
Okay.
So I just want to show. So, so, so first we have the double bond equivalent. It is equal to 2 multiplied by 2 minus x plus 2, and all of them is divided by 2, and the answer is 1. So the number of the one is the number of the in saturation, which means you will have a circle or a double bond.
Mm-hmm.
So first, it done so when it pick around 10 to 13. So it is not the carboxylic acid. And I see a peak around 3.5 to 4.5. So it is ester. It is an ester.
You mean this one?
Yes. Yes.
Yeah.
Yes.
So you say what did you say?
Because it's so big here, so it may be ester.
But how an ester is something like that?
Yeah.
So here, if I write only this, I don't see any proton on this. So what do you mean? What should I write?
Next to the oxygen, it will have CH3.
Like that?
Yes, so it will show a pic. No. And then next to the C, we'll have the CH3 and CH2. CH2 is CH3. So the CH2 here will have a label. I don't know. Oh my god. Sorry, a little bit.
Well, the idea is good for this group. I agree, but the chemical shift of this kind of CH2 will not be so deshielded at 4.1. It will be around something like that, okay, around 2.5. So as it is at 4.1, what do you think?
Oh. Try again.
Because of the chemical shift of this signal, the CH2 is not close only to a carbon and a double bond, because if you look at the table, it will be around 2.5, something around there. As the chemical shift here is 4.1, then the CH2 should be there.
Okay.
Okay? It's because of the chemical shift. But you are right. This CH2 should be close to CH3. Okay, here you have 2 protons, so this is a CH2. Here you have 3 protons, so this is the CH3. As if we could measure the coupling constant, we will see that this coupling constant will be the same as in here. So they are closely related. They are close together. So because we have a CH2 as a quartet and a triplet and a methyl group as a triplet, they should be closely related. And because of the chemical shift, the CH2 should be close to an oxygen. Okay for everyone?
Okay.
And what did you found for this signal at 2 ppm? Anne?
Yes.
Yes?
Signal for the 2 ppm is the C. It is simple, so it is the signal with the CS3 next to the ester.
Yeah. Yes, because it's closely related to the C double bond O, then the chemical shift is a little bit higher than a classical methyl group. Okay, so that's why it's around 2 ppm, and the other one it's only at 1.5, 1, 2. Okay,
Yes.
so if I swift, I will. And then you have the solution. So the structure is ethyl acetate, right?
Yes.
Yes.
So it's good. So be careful. You understand well how to use the multiplicity and the coupling constant, but be careful about also the chemical shift. It will help you to uh, uh, add properly the heteroatom, for example. The next one, who want to try? Nobody? One, do you want to try?
Okay. First of all, we can consider this one doesn't have any double bond or the cycle.
Yeah.
Yes. So first we have the chloride atom connect to a carbon.
Okay.
Uh, Due to the signal at I think about 3.2. I think the carbon that was the carbon with the two hydro atom next to the chloride. So it should be a CS2.
Okay.
We have the 9H at the same signal at the 1.5.
Mhm.
So I predict that there are 3 carbon connect to one single carbon. So upon the structure, we connect the one carbon to the last one, and then we split the three part. The three, yeah, we have 3 ways. All 3 of them are CH3.
You mean something like that?
Yes.
How do you call this chemical group? This.
Okay.
How many carbon do you have? 1, 2, 3, 4.
5. There are 5 carbons.
No, for this group with the 3 methyl group, this one, how it is called in organic chemistry?
Mm,
How many carbon do you have there?
there are a total of 4 carbons.
Yeah. How is it called?
Mm,
It's a butyl.
yes, a good team, but it is they charm.
It's a tertiobutyl group. Okay?
Yeah. Okay.
Yes, that's right. Maybe I should explain for everyone. So we have to consider that all the signals are singlet. As they are singlet, that means that they are not close together. So I have to find a way to separate them with an heteroatom or quaternary carbon, for example. So that's why I have no several solution. I have only one, which is to have only one CH2. As the chemical shift is relatively high, around 3.1 or 2 ppm, then effectively it's close to something that de-shield the chemical shift of a classical CH2. So this is the chlorine. And the other group, I should draw 9 equivalent proton. 1 carbon is not able to wear 9 hydrogen, so I have to find another way. And as I have 5 carbons, that means that if one is here, 4 others are in the last group. So that's why I draw this like that. It's the only way to have 9 equivalent proton is because we have 3 equivalent methyl group on the carbon, which is a quaternary carbon, no hydrogen here. And so we have a singlet for this group, and singlet for all these group. Okay, for everyone?
Okay.
Yes.
Yes. Okay.
And if I wrote this, if I have this, what should be the spectrum? What should I find on the spectrum? How many different group of proton do we have in this structure?
We have three different groups.
Yes, we have these two, which are always, again, equivalent. We have the blue one, and we have the methyl group, which are equivalent. Okay, for everyone?
Yes.
So how many signals should I find on the spectrum?
There should be three signal.
Yeah, we should find three different signals. And what would be the shape of each signal? For the CH2, for example.
Think there will be only like still one straight line.
You mean a singlet?
Yeah, the singlet.
The other people? What do you think?
I think it will be doublet
Why?
because for the you mean for the CSU, right?
Yeah, for this one.
So it
For both.
will so it has a naval electron naval electron.
Yeah, on the carbon B side, we have one extra hydrogen. So this group, the CH2, should be a doublet integrating for two hydrogen, right?
Yes.
Hong,
Mm.
is
Yes.
it okay? Is it okay for you?
Yes, it's okay.
Yeah. It's a doublet here. For the two methyl group, do you agree with me that they are equivalent, both of them?
Yes, I will.
Yeah. So what would be the signal for these? I will have a signal for 6 proton this time, not 9. And what will be the shape? And the question is,
I think the doublet.
yes, it's also a doublet for the same reason. Here on the carbon beside, we have an extra hydrogen, right? So here on the spectrum, we should see a doublet here for the CH2. And here we should have a doublet also for 6 proton. Okay, for everyone. Just
Okay.
I try to. It's not very beautiful, but okay. And what about the blue proton?
And you have a singlet shape.
A singlet. Are you sure? How many carbon we have around? I have 1, 2, 3 carbon around. And how many protons on all these carbon?
There are total of 8 protons.
Yes, 6 plus 2. That's 8 protons around. oops. 8 protons in the neighborhood. We are in an aliphatic molecule. We have free rotation on around the bounds. That means, and the distance between each groups and the proton is 3 bonds. 1, 2, 3. 1, 2, 3. 1, 2, 3. So we have the around approximatively the same coupling constant with each between all of them. That means that I should use the relationship m equal n plus 1. I should find 9 lines in the signal. Okay? So it's some, we will call that a multiplet because it's too complicated to identify properly the signal. Okay, for everyone?
Okay.
And what will be approximatively its chemical shift? Is it over the CH2 or lower than the CH3 or between both? It will be between both. Not, I don't know exactly where, but as what we have to consider is the distance between the blue protons and the chlorine atom. The closest group to the chlorine is the CH2, so it's strongly deshielded by the influence of the chlorine. The CH is one bound far away from the Cl, so it will be also deshielded, but the influence is less. And far away again, the two methyl group are around 1 ppm. Okay for everyone? Yes, no?
Yes.
Yes. Yeah, okay.
Okay. Okay, in this document, it was the only exercise I gave you, and in the other, it's let me stop this. Non, c'est celui-là. Which file did I give you for the next exercise? I don't remember. Can you just tell me? Was it that one?
Yeah, so the name of the file is PP20 exercise NRM version 3, right?
P and G. Ah, yes.
The
Training. Yeah.
chain.
Yes. With only aromatic proton, right? Rotation. Where is it? I can't see it. Why it is not possible to share a PDF document? That's strange. Ah, see. Do you see it?
Yes.
Okay. It's that one I gave you?
I think
Oh, yeah,
those.
yes, I saw it.
Yes.
Well,
Yes. Okay. So, who want to try? Mm-hmm. I will not be able to write on that one. Because it's a PDF. I can't use my the style. How can I do that?
Maybe you can copy the image to the
Yeah,
paint
that's what.
or something.
Yeah, that's what I was thinking about. Okay. So did you try to work with that one? Hello? Are you still there?
Yes,
So what can you say about this molecule?
hmm, I think this molecule contain an aromatic ring.
Yeah. Because the chemical shift we can observe are only between 6.5 and 7.5. We have no other signal anywhere in the spectrum. So yes, I agree. What about if did you calculate the double bound equivalent?
No, I haven't.
is 5.
Yeah. So what does it mean? How many in saturation do you have in an aromatic ring? How many in saturation? Because we don't have to consider only the double bond, but also the cycle. So in an aromatic ring, I have 3 double bond and a cycle. So the aromatic ring is already considered to
5.
4. The cycle and the 3 double bond.
Okay.
Okay?
Okay.
So that means that in the structure, we need to have another group, a chemical group with one more double bond. Okay for everyone?
Okay.
Okay. So come back to the signal. We have, how many different signals do we have? How many
There are 8 signal.
Yeah, but what I mean is how many different chemical shift. That mean, I mean, how many different group of protons?
There are 3 different groups.
Yeah. So I have one here, the other here, and another here. So, okay. And it is said here that I have 3 protons. Each signal is for 1 proton. So that means that on this aromatic ring, I have 6 carbon, but I will have only 3 protons. That means that I should have 3 different substituents. Okay?
Okay.
And substituent. And in this substituent, I have to find 1 double bond. Okay?
Okay.
So let's go further to, we write only this part on the spectrum, on this picture. So we see now better the shape of each signal. So this is one chemical shift here, and this is the other here. Right?
Yeah. Oh.
Okay. So if we want to describe this signal, can you tell me what you see? We will make some different color. I wrote in black the aromatic ring here. So let's say for this first one, what can you say? What is the shape of the signal?
The first one, the shape is the doublet.
Yes. And this one?
The second one is quartet.
Are you sure? Remember what we said last time? A quartet should be like this. with the same, it's the same coupling constant between each lines. And that means we have a coupling with 3 equivalent proton.
Yeah.
And the 2 lines in the middle are 3 times higher than the line in the side.
Okay, so
It's not the case here, right?
so in this case, I would say it's 2 different doublet shape.
The integration said that all this is for 1 proton. Remember, we work at the end of the lecture last time, we talked about the value of the coupling constant in aromatic ring. We talk about the coupling ortho, coupling meta, and the coupling para. And because of this, on an aromatic ring, we have to consider the distance between the proton, and this distance will give us the value of the double bond. And as soon as you have the protons are have different distance between them, the coupling constant will be different. So here we have a double doublet. Remember? Double doublet means that we have a coupling with 2 different protons, and each of them has its proper coupling constant. Right?
Yeah.
So here the signals we should have all the line with the same high. I agree. Okay. But in practice, this is not exactly the case. I will not explain why, but usually when the signals are close together like that, we have what we call the roof effect. We call that like that because you see we can draw something like that. That means that these 2 groups of proton are coupling both together. But what is important to keep in mind is as soon as you cannot see a quartet like that, all the characteristic of the quartet, then it's not a quartet, but it's a double doublet. You see, I have 1 coupling constant here. I can measure the same here, and I have a bigger one that I can measure between these 2 lines or between these 2 lines. I have only 2 different coupling constants. So this cannot be a quartet, but it's a double doublet. Okay. And the last signal, what is the shape of the last signal? At 6.72, 3.
For the last signal, it is a double singlet.
No, it's a doublet.
It is a double. No, it's a double. I mean, they don't like feel like a coupling. So I think it's a 2 different.
But it's important to keep in mind that they give us the value of the integration. They could not be 2 different signals because I have only 1 proton for from here to here.
Okay.
Right?
Okay.
And also the other thing we have to see also is just when we calculate the coupling constant, this constant is found here also. I have the same here or here. Okay?
Okay.
So that means that these two groups or these two protons are coupled one to another or are coupling one to another. And if I change the color for this, and this coupling constant is found here or here. So that means that this proton in the middle is coupled both with the red one, for example, and with the blue coupling constant. But they are separate by a different a number of chemical bonds. Right? Alors, let me change the color. This one will be the blue one. And the other will be the green one. Okay. The blue and in the middle will be the red one. So if I start to write on the structure, let's say I write the red one. This one should be a double doublet in the spectrum with a chemical shift of 6.92, 93. Where should I write, sorry, the blue one and the green one on this structure? Can we calculate the coupling constant? How? How can I calculate the coupling constant? For start by the green one. Remember, we said that the coupling constant is equal to the difference between the frequency of resonance, right? But here we don't have the value of the frequency, but we still have the value of chemical shift. And remember, I told you that we can use the chemical shift, but we need to know the value of the B0 field and divided by 10 power 6. So here, if we make the calculation, the coupling constant will be 6.74911 minus 6.7040. What is the value of B0 here? It is given here, 300 megahertz. So make the multiplication by 300 and I divide everything by 10 minus 6. So what is the value? Can you do the calculation or have you done the calculation? Hello? It's a little bit high. 74 minus 6. 70. Hello, did you make the calculation?
I think the result is 4.45 multiplied by 10 power of minus 6.
No, there is a problem. 74,911 minus 6.7465 cross 300 is. So I think it's the field here is not 300, but it's 200 because it's too high. So it's around 7 hertz if I remake the calculation. 76.7. It's 8.89 hertz. And that means it's equal 6.9, 8.9 hertz. Okay? Yes or no?
Okay.
So here the coupling is around 8.9 hertz. What about, can you make the same calculation for the blue one and for the red one, please?
For the blue one, it is the 3.05.
Let's say 3.1 hertz. And in the red one, So the first one, the small one you can calculate here or here. And the second one will be here and here, or from here to here. Okay. What are the value?
The one is 2.464.
Mm-hmm.
464 is around 2.5. No, I mean the Z1 is nearly 2.5, not 2.6.
Mm-hmm.
For the
Excuse me.
is
2.5.
yes, and for the page 2 it is nearly 8.3.
Okay. Maybe we can calculate with the others. This part of the signal 6.9433 minus 6.8890. When I take these two, I have 3.1. And if I take this and this, I have 6.93, 3, 3, 4, 6, 8, 8. It's 8.8 here, 8.8 hertz. Okay, nearly 8.9. So as you could see here, we found in this signal both the coupling constant with the blue one and the coupling constant with the green one. Do you remember the value of the coupling constant in aromatic ring? What is the value for the J ortho? Remember, we said it's between 7 to 9 hertz. A coupling meta, it's between 1 to 3 hertz. And G para is less than 1 hertz. So that's why we don't see it usually. So here, as you could see when you measure the value on the spectrum, we have one coupling ortho with the green one and a meta coupling with the blue one. So can you think about this? A few minutes, I come back. I have to see my student in the lab and I come back in 2 minutes. Hello?
Yes.
Yeah. So can you tell me what you found? How can you draw the blue proton and the green one? Maybe. So the question is, well, the green proton here is a doublet. That means that it is coupled to only one proton, or at least with a strong coupling with an ortho coupling. So as I found the same coupling constant in the green one, 8.9 here. So then in ortho position close to the green one, the red one, I should draw the green one. Doublet with ortho coupling. Is it okay for you?
Okay.
And where is the blue one now?
The blue one is just the para position.
I'm sorry, I didn't understand.
I think it is at the. I think it is at the para position
Para position from which one?
from the red. From the red. one.
Here?
Yeah.
Do you mean here?
Yes.
Do you think in the red proton we have a para coupling? We said that para coupling is less than 1 Hertz. Do we measure a para coupling here? Here we have 3, 2.5 or 3.1. There is no para coupling there, okay? So, and if we keep this position, what would be the shape of the green one? It will not be only a doublet. It will be a doublet with an ortho coupling, but also a doublet with a meta coupling with the blue one. And the green one would be the double doublet, and here we would have only a doublet with an ortho coupling. So it's not good like that. So where should I write the blue one? The blue one doesn't have any interaction with the green one. So that, or if it has one, it should be very low or small interaction. So that means that maybe it could be here in para of the green one, but in meta of the red one. So the red one is the only proton to be under a doublet shape. Okay? And the blue one is far from 1, 2, 3, 4 bounds from the red one. Then this is a coupling a meta value. Okay? Everyone?
Okay.
now, when we look at the formula and we compare with what we have drawn yet, the aromatic ring is 6 carbon, and we said that we have only 3 proton on the aromatic ring. So it is left 1 carbon, 3 hydrogen, and 4 oxygen to complete the structure. And this should be the substituent. What kind of substituent or chemical groups can I write using 1 carbon, 3 hydrogen, and 4 oxygen? And remember, I must have 1 in saturation in this substituent. What kind of substituent can I write? I need a double bond, so I can propose a COOH. So this is for 1 carbon, 1 hydrogen, 2 oxygen. And it is left 2 OH. And I have 4 oxygen and 3 hydrogen. Right?
Oh, yes.
But where should I write this? I have 3 potential positions for these chemical groups. It will depend on the chemical shift of the different protons. The blue one is the more deshielded. And then the red one, and then the green one is the more shielded group. So that means that the more deshielded proton, most deshielded proton, should be close to a deshielding group or withdrawing group. And remember that the carboxyl group is a very strong withdrawing group. So that means that the blue one should be close to the carboxyl group. So the first proposition could be writing the COOH there, because these two are more deshielded, and then the 2 OH there. Do you agree?
Yeah, I agree.
And the other people?
Yes, it's okay.
But this is not the only possibility, right? I can draw something different. Pardon. I can also draw this, but to be sure and make the choice, we need to use some table, but we will don't do it together. It's a little bit earlier, maybe next time. I will send you the table. We can use with many, it's a table where we have the chemical groups here. So for example, COOH, OH, CH3, 3 double bond CH2 and so on. And then we have the effect, the quantification of the effect of each chemical groups depending on the position of the protons on the aromatic ring. And using this table, we are able to make to calculate the theoretical value of the chemical shift, and then make the choice between different possibilities, different structures. We'll try to do that next time. What time is it? Okay. Maybe we can do another exercise. Yes, maybe we can go on with this, in fact. Let me just add start here, partager. Do you see it again?
Yes.
Ok. Pourquoi je peux plus effacer? Alors, okay. So we just try. I don't know if you remember. Your organic chemistry lectures. Do you remember them? When we work on aromatic ring, remember we put the proton like this. And we said the COOH is there, OH is there. And the other side, we can draw the other structure. And there is a third one. And we try to do that with only the value. Do you remember when we want to draw the influence of chemical groups with the electrodonor or electroattractor effect. We used to draw these small signals, for example, delta plus, delta minus. Do you remember that? In organic chemistry, for example, an hydroxyl group has two doublets of electrons. The oxygen is more electronegative, so it's a withdrawing electron, but we have a strong mesomeric effect. So we say that hydroxyl group are the electron donor effect. So we will have a delta minus, a strong delta minus effect here on this position also. A small, let me see, a small electrodonor in para, but we have remember, because the double bond is going there, then it's going there, and then it's going there. Do you remember that? No? Hello?
Yeah.
Should I go on or should I stop there because it's too complicated?
Yeah, I think you can go on.
Okay. So for this hydroxyl group, I can draw the same things. Delta minus in ortho and in para, but delta plus in meta position. And for the carboxyl group, let's say it's a orange. The effect is a withdrawing effect, but a mesomeric withdrawing effect because we have a CO double bond. So we will have a strong delta plus here and here. In para, a small effect, but we have a small donor effect in meta position. So when we make the addition of all the effects for each protons group, which is what we are interested in, we can see that a strong delta minus effect is overlaps with a small delta minus effect. So we have here a strong delta plus. Here we have a small delta plus effect, and for the other we have a strong delta minus effect. That means that if theoretically I look at the spectrum, I know I am in an aromatic ring, so the mean value for aromatic proton is 7 ppm. So that means that around this value, theoretical value, I should have a proton which is a double doublet that is strongly deshielded. Then in the middle, I have the doublet with the coupling meta, and strongly shielded, I should have the proton with the coupling ortho. Okay? Is this what we have on the spectrum? No, because the double doublet should be in the middle. So this position doesn't seem to be real. So for next time, I will let you do the same for these two other structures. Did you draw them on your book note? Hello? Hello?
Yes.
Not yet.
Okay, I will let you do the same exercise with these other two structures. So next time we will compare the three structures and we will choose the best regarding the reality. Right?
Okay.
Okay. So maybe we can do the last last exercise before we go away. Yes, I will do that one. Did you try to do this exercise or you didn't? Do you see the slide?
Okay.
Okay. So again here the field, the B0 field is 200. Okay, so what do you see on this spectrum? We have 2 peaks of solvent, so we don't need them. And how many groups of proton do we have and what are the chemical shifts? So what is your conclusion? Well, again, here we don't have a lot of signals except this one between 6.3 and 7.5. The integration tells us that we have one signal integrating for one proton, and it is a triplet, and a second group integrating for two protons, and it is a doublet. So here we are in an aromatic ring with two protons. Aromatic ring means 6 carbon, and I have only 3 protons. So if I make the delta between the crude formula, it is left 1 carbon, 3 hydrogen, and 4 oxygen again, corresponding to the substituent group. Okay. Can you calculate the dBe again? Please. Again, it is 5.
It's 5.
Yeah. And as before, we know that the aromatic ring corresponds to 4 double bond equivalent. So it is left 1 double bond for the substituent. Okay. Next step, we should calculate the coupling constant in the triplet and in the doublet. So then we go to the biggest figure. So can you calculate the coupling constant? Remember, in a triplet, we have twice the same coupling constant. So even if we don't have the value of the first peak here, it doesn't mind because I have the others, the others. And if we calculate 7.2356. It is 8.4 approximately, and if I calculate here, it is 8.4. 2. So the coupling constant is of what type? Is it orthocoupling, metacoupling, paracoupling? Hello?
It is orthocoupling.
Yeah. So, what can I draw? How should I draw the proton on the structure? What does it mean that we have two protons, two equivalent protons on an aromatic ring? What does it mean? How can I?
They should be in the same position. So if I'm gonna interpret this one, we have the two hydro at the ortho position.
I'm not sure I understand what you want to say. Just try again, please.
So the have the two proton at the ortho position.
If I draw one here, this one,
Yes, yes,
and
and the two position next to it also.
like this.
Yes,
Okay. So where is the triplet?
the chip. Uh,
The triplet is the hydrogen in the middle.
Yeah. And here we have a doublet, and here we have a doublet. But how can they are on different carbon, so how could they be equivalent? Because they have the same chemical shift. That means that in the structure, they have the same neighborhood, the same kind of chemical groups around. How can I draw that? You know that for the substituent, I have 1 carbon, 3 hydrogen, and 4 oxygen. So what kind of chemical group should I have with 1 in saturation? Again, as before, I can draw a COOH and 2 hydroxyl group, right? And now, how can I draw this group on the structure to be sure that we have 2 equivalent proton there? Please make some proposition.
I think the COH in the para position of the triplet hydrogen.
Like that?
Yes.
Okay, so what can we say? That's right, okay. But that means that we have an axis of symmetry in the structure. Okay, for everyone. So that's the only way I have to draw the structure, to have 2 equivalent proton on an aromatic ring. If you see signals integrating for 2 protons on an aromatic ring, that means that you must have a symmetry in the structure. That means that this proton and that one has exactly the same influence around, so they will have the same chemical shift, the same frequency of resonance, and the third one is alone in the middle. We have only 1 proton. Do you agree with that?
Yeah.
Yes.
Okay.
Okay, so really think about symmetry when you have equivalent proton in aromatic ring. Okay, so for today we will stop there. For next time, tomorrow morning, let's say that we start again at 30 past 4, past 2 for you. Okay, I'm afraid I won't be on time again. So let's say as soon as I arrive, just like we did today, I switch on. Okay.
Okay.
So tomorrow morning it will be a lecture on carbon 13. So we will see a few things to keep in mind for carbon 13. And if we have time, we will come back to the exercise we did before. Okay, on that one. Okay. Yes or no?
Yes, it's okay. And can you send again this exercise because I don't see it in the mail?
Okay. Okay.